Welcome to Breadboarding. In the previous video, we introduced the CGA video controller and I went through some of the background to it. So if you haven't seen that video, it may make more sense to have a look at that video first. There'll be a link in the top right hand corner of the screen up here, and that will actually introduce you to the background to the video card and the various components that we're going to be using. And we laid out the breadboards in a similar layout to what we did in the version 1 Breadboard PC. In that case, the CGA video card stretched over 7 breadboards. So you see 1, 2, 3, 4, 5 across here, and then 2 down the bottom here. And this is where the video RAM was and the various control logic around here. In particular, when we tried to eliminate the video snow, so the screen flickering and interference you get when the CPU updates the video RAM at the same time that the display is using it. And this is a fairly complex bit of logic down the bottom here. So what we're going to be doing is replacing a lot of the chips over on the left hand side here with these complex programmable logic devices, CPLDs, the ATF1504 that I introduced in the PLD series. Again, there will be a link to the top right hand corner here to the PLD video series, and this covered how to solder one of these 100-pin thin flat pack packages to one of these 100-pin adapters, and also the same chip comes in a 44-pin variant, and this was soldered to a 44-pin dip adapter. So this version is slightly easier to use, however, only a proportion of the 64 macro cells are available on pins here, whereas with this one, all 64 macro cells are available on pins. So we're going to be looking to see if we can squeeze with these two chips here, if we can squeeze all the functionality into fewer number of breadboards. In particular, get rid of the 2 down the bottom here. So this is video 12 in the Breadboard PC 8088 version 2 series. And this is the original CGA video card that I covered in the previous video. Again, there will be a link at the top here to link back to the first video on the CGA card. And the original IBM CGA video card was released in 1981 with the IBM PC. It used the Motorola 6845 cathode ray tube controller chip, had hard-coded character fonts in ROM, had 16K of dynamic video RAM, had a composite video output which could also be used to feed into a TV via an RF modulator, and it had TTL level CGA video output that would go into a compatible monitor. Now these monitors aren't easily available these days, and so what I covered in the previous video is redesigning this card to produce more modern VGA video output that can go into more modern video equipment and video capture hardware. And you'll see down the bottom, the original CGA card was 69 chips in total, and 59 of those were basic TTL logic chips. This is a high-level plan. We've already done the first third here, where we produced the basic Nanocomp 8088 computer that used the LED display and keypad. Now we're coming to the end of our basic floppy disk PC. Once we've done the video controller, we then just need to do the floppy disk controller in order to be able to boot MS-DOS off floppy disk. And then we're going to go on to add a hard disk and enhance the video adapter to do all graphics modes. We'll add a mouse and then try and boot early versions of Windows. So I covered this in the previous video, but what we're going to be doing first of all is installing the cathode ray tube controller. And the reason why we need to do this is because this produces the horizontal sync and vertical synchronization signals which are needed to drive the video display. We're going to need our basic clock here. Now we're going to be combining many of the PLDs into this one ATF1504 PLD, and we're going to be using this 25.175 MHz dot clock. So this is the lower of the 2 frequencies that VGA was able to do. I think there's another frequency around 28 MHz as well. We're going to need to also do the I/O port decoder so we can address the CRTC, and we're also going to be installing the video digital analog converter. So this is a IMS G176 chip, which you can still get second-hand today. This is one of the few chips which isn't available brand new, I believe. But this actually provides a VGA-compatible output stage that is able to actually produce the VGA 0.7 volt output levels that we need to drive a modern display. And what we're going to be doing here is, because we don't have any video RAM or anything else to feed this DAC to start with, we're just going to take some of the address lines coming out of the CRTC, feed those in as the data for the video DAC. So we're using that to generate a colour pattern output on the display. Our memory map here is basically the standard CGA memory map, but we do need to also initialize our video palette over here. Now, the BIOS that I did for the version 1 of the Breadboard PC has already got all these changes in it, so there shouldn't be very much we need to do to get all this working. And this is the pattern that we'd expect to get out here. So we should be seeing the 16 CGA colours, and depending on which of the address signals we choose, then we'll get different size blocks coming out in this sort of test pattern. And this is just to allow us to verify that we're getting the output that we'd expect. So I've done quite a lot of work on the KiCad schematic to simplify it. Now, to start with, what I did is I took a screenshot of the diagram, and this area surrounded by blue are all those chips which are going to be replaced by our 100-pin complex PLD. And you can see down the bottom here the KiCad schematic had already created a symbol for this. And basically the main effort in this part of the project has been to work out the optimal pin layout for this chip here and to work out how to replace it, then to actually copy in all of the PLD configuration logic for these chips into the configuration for this one. So here's the schematic. You can see that this is our 100-pin chip here, and over here is our 44-pin chip. So this is replacing 2 PLDs and a flip-flop. And this one is replacing all those chips that are surrounded by the blue border. If we drill in here, what I've tried to do is to make this as similar to the breadboard adapter that we've got. Now, the breadboard adapter does actually have 2 rows and columns of pins here, so the inside pins tend to be the even ones and the outside ones tend to be the odd ones. Now, on the vertical even ones, those will actually plug into the breadboard, and so it makes them a little bit easier to wire up. So if we start from the VGA video connector backwards, so we need to ensure that we have a constant current source for our video digital analog converter. This provides a standard current reference to produce the voltages out here, and we will have a small adjustable resistor here so we can adjust the intensity of the output there. I've moved things around quite a lot on the board to try and make it fit a bit better. So now we've got the cathode ray tube controller chip is actually up on the top here, together here to make wiring things up a little easier. The video address logic, so we have the main address bus coming in here. We have the CRTC video address coming in here, and then the address lines here are then going into the video RAM chip. So this video RAM chip was on the 2 boards at the bottom of the design in the version 1. Now I've managed to combine all this up onto the same board here. We've still got this 646 bidirectional buffer latch. I suspect that with a bit more effort I could probably merge this in with this here, and certainly there's a 1508 chip that has 128 macro cells. If I was using that, I almost certainly could probably merge this chip and this chip into here as well and simplify the logic even further. So down the bottom here we've got our character generator EPROM. So this used to be up towards the top of the board. The shift register here takes the raster output of the character generator here, and it also takes the high resolution 640 pixel data out of this latch here and also serializes it. This is our 44-pin complex PLD, which now replaces 3 of the chips from down the bottom here. Now what I have done is also put the JTAG programming port on here, and so in fact this port is connected both to this chip, and the TDO and TDI inputs and outputs of these chips are chained together such that this will be chip 1 and this will be chip 2. We've got our data bus buffer, our address decoder. Now some of the address decoding has been moved down to here as well, and there was a separate PLD here, so that has now been merged into here. And then we're back to our video address buffering here. So the design's quite a bit simpler. Ultimately, I think with the 128 macro cell version of this, we probably could get rid of this one here and possibly this one here. But these address buffering and decoding chips are probably not going to be worthwhile replacing. The way how this has been laid out here is pretty close to the breadboard layout, so I have tried to make sure that this layout here indicates the number of wires which are going to be going between the various chips. It just helps to simplify the wiring up of this. So if we take a look at the revised breadboard layout, so you can see now we've got rid of the two breadboards. So these two breadboards which are down the bottom here have now become unnecessary. So we've got the 100-pin TFT adapter here, the 44-pin one here, and the JTAG connector, programming connector, will go down here. And the only thing I did need to do is to add in this extra bus rail here. So this extra power rail here widens the gap between the breadboards, so this adapter will actually plug in. So the inside pins here will actually plug in either side here. So now we need to go off and wire all this up. So I need to put some power rails along the top here. I'll probably plug most of the chips in. I'm just not going to wire the majority of them up. I'll just wire them up as I need them. So I've put in all the chips and I've got chip labels on them all. Put in these power rails at the top here, power rails down the bottom, and just join this power rails together. I've got a power connector to put in here at the top once we've wired everything else up. Now I'm not going to put the 100-pin CPLD in quite yet because, as you can see, with all of the various wires for power and whatever, it does tend to get in the way a bit. So we'll just leave that here. There's a few wire links I've left here just to make sure I put things in the right place when we come to put everything in. So the first stage, we're going to be needing to wire up the connector over here. That's the VGA connector, the video digital analog converter, CRTC, the I/O port decoder. We are going to need a couple of signals out of this to do with the clock, certainly the character clock and the dot clock we're going to need out of there. So I'm just going to now wire that up. We'll go through looking at the circuit diagram as we do that. First we're going to wire in the VGA connector there. So you see we've got the red, green, blue values, quite a few ground values, the vertical sync, horizontal sync with a couple of resistors in there as well. That's the red, green, blue video signals, then plenty of ground signals there. There is a 5-volt one, but we're not connecting that up for the moment. Then the two resistors for the horizontal sync, vertical sync. Then we're going to wire in the red output from the video DAC, but we just want to put in these extra ground connections here first. Then the green and the blue. Now we need to put 75 ohm resistors in here to make sure the impedance is balanced with the VGA connector. Now we're putting in the constant current source. Now this is where I made a slight mistake here. So when putting in the yellow link there, it should have been going to the diode there and not to the resistor. So I found that out in testing. Now we're going to connect up the various ground rails, tying inputs to ground and connecting the address A0 and A1 lines. We're also going to be looking at the read and write enable for the video palette as well. So just putting in tying the unused inputs to the video DAC to ground, then putting the address lines around here. Now the only issue here was that chip isn't being used at the moment, so I did need to hook up some additional address lines there until such time as we enable that chip. So now there's display enable and connecting the data lines between the two chips here. Display enable goes into the blank input. So this just means that the data lines are connected together and we just need to put one connector in there. The blank display enable, power. So now we're going to do the palette read and write, the chip select for the 6A845, and we also need to do the E-clock signal as well. The chip enable, in fact, the label on the chip there was incorrect, so I needed to move that up a bit later. And in fact, also the I/O write there should have been going down one extra pin as well. Now we're going to hook up the JTAG programming connector. The ground, there's two outputs there need to have pull up to 5 volts or it won't work. So we've got the clock, TDO, which is the output, TMS, which is a kind of a select, and TDI is a input if we've got more than one chip. And then there's all the ground the internal 5 volts and the I/O 5 volts we need to connect up there. And they're also going to need to hook up the video horizontal sync, vertical sync, and character clock there, and send the output to the vertical sync, horizontal sync to the connector. So just wiring in the ground 5 volts and I/O 5 volts. This is a bit fiddly and a bit messy with these types of connectors. So now we're going to connect the JTAG clock. This is going to an even pin, so the even pins are on the inside and are actually connected to the breadboard. Then TDI. Again, this is pin 4 over there, so that is actually connected to the breadboard as well. So we'll just bridge the gap there, and that can go straight to the breadboard there. And TMS is actually going to go to pin 15, so this will be one of the pins actually sticking out. We're just going to use a fly lead there for the moment. Then TDO goes to pin 73, which again is going to be one of the connectors sticking up. Okay, so this is the current state of the board. So once I'd finished wiring up the ATF1504 over here, I plugged in the JTAG programmer and I was testing out the chip and the programming of the chip, trying various clock signals. So I put a temporary 25 MHz oscillator in here to test out the dot clock. This will be coming from the main board once I've plugged it into the main PC. And to cut a long story short, I've switched over to an ATF1508, which is a 128 macrocell chip, and I'll just explain the reason why. So this is the output fit file from the 1504 configuration for the CGA video. And if I just take you through this, I have covered this in great detail in the PLD video series. So video 9 of the PLD Programmer Logic Devices series. There'll be a link for it up the top right hand corner of the screen there if you want to go off and see some of the detail on this. Even though not all the pins were being used, because of some of the internal logic rules, then I was using up to 90% of the resources of the device, and the fitter recommended using a larger device. And when you get down to the bottom of the fitter file here, you can see that we're using all of the logic cells. We're using a lot of product terms here. And in fact, the fan in and the fan out. So the fan in, I think there's a maximum of 40 terms in a fan in. So it's getting pretty full. And so I took the decision to switch over to an ATF1508. So that PLD 9 video covers some of those aspects. So what we're going to do now is we've got the 25 MHz dot clock here feeding into our 1508 PLD. So I'll modify this now to be a 1508. And what we need to do is to test out that this chip is actually producing the character clock, so the 3.1 megahertz. This is 25 divided by 8. And then the horizontal sync and vertical sync signals going through here are then actually coming out okay over here. So I can test this out in isolation from the main board, but then what we're going to need to do is to plug in the address and data line so we can program the CRTC and check out the I/O port decoder. But I just wanted to check out that the PLD was working properly first. So what we're going to do is to wire up the 25 megahertz clock here to the input global clock up here. I'm going to wire in the logic analyzer to provide the 2 sample horizontal sync signals, so about a 70 hertz vertical sync and a 15 kilohertz horizontal sync. I'm just going to make sure then that the output signals coming out of there are okay. So once we know that this chip is behaving itself, then we can wire in the rest of the data bus, address bus, can actually start testing out that we can get something out of the video here. Okay, so let's take a look at the logic analyzer. So we have the clock output, so we've got a 31.5-ish kilohertz with a 5% duty cycle, so that's our horizontal sync. And the 70 hertz with about 10% duty cycle, that is vertical sync. And these will be active high. So we're just going to set this to about 200 megahertz, about 20 million samples, and we have got some glitch filter settings here we might need to adjust. So now just going to record this Okay, so first of all, we can see that we've got our vertical sync input here, and if you look on the right hand side over here, you can see that that is about 69.999 Hertz. And if we drill down to look at the horizontal sync, we can see that that is about 31.47 kilohertz, and the duty cycle. Now, what you can notice here is that the output horizontal sync is inverted, because that's how we've set this up. For the 70 Hertz sort of 400 lines for text mode, we actually need horizontal sync to be negative sync, so that means it's active when it goes low. And so if we also now just add some timing markers, we should be able to see as well that the horizontal sync and vertical sync should also be delayed slightly. Now, under normal circumstances, this should be exactly 1 character clock, because the frequency generator in the logic analyzer is not tied to the character clock, so it won't be exactly 1 clock cycle. But we can see here we've got a delay of about 200 nanoseconds, so if the clocks are synchronized, this would indicate that we have got the clocks being delayed. And similarly, if we look at the vertical sync, we should be able to see that that is also delayed. You can see that that's also delayed, not quite as much as the other one due to the differencing in the timing there. So as far as the other signals, now the dot clock, the logic analyzer is having a little bit of trouble picking up the dot clock from time to time. But if we have a look at the oscilloscope on the dot clock, we can see that the signal appears to be fairly clean. There's no real major interference on it, and you can see that it's about 25 megahertz there. So the dot clock looks to be okay. Just depending on the glitch filter settings and the frequency we're scanning this at, then sometimes it can miss the odd cycle. Now we can see down the bottom the QA, QB, QC is the dot clock divided by 2 and divided by 4 divided by 8, and then also divided by 16. The divided by 16 is used when we've got 40 column mode. I can see that the cycle here, the dot clock cycle 0, 1, 2, 3, 4, 5, 6, 7. This is the cycle, and the character latch and the attribute latch are actually then coordinated with those. Just need to find a clean bit of signal here. So you can see here that the character clock is in fact actually the inverted QC, because the CRTC actually needs the inverted clock in the original CGA design. And we can see really that the QA, QB, QC goes from 0 to 7, and that we can also see that the character latch is also then occurring at this point here, and the attribute latch is occurring at this point here. So there's normally a rising clock signal. Period here goes from 0 to 7, but in fact it's the character clock, not the QC, that determines this. So in fact the timing of this we'll need to check when we've actually got this all hooked up. The character latch will actually load the current byte value for the character data into the latch that will then access the character generator ROM, which will then provide the raster image for the character. And then the attribute stroke shift register latch, this will actually provide the second byte of data will be latched into the attribute latch, and will also take the raster data out of the character generator at ROM and will feed it also into the shift register. And then the character stroke attribute value here, this is related to the character clock, and QC is delayed slightly, and this basically toggles the address of the video RAM between the character and the attribute bytes. So it looks like the signals coming out here are looking okay. You may need to tweak things a little bit, but the configuration here has come from the previous CGA project, so I'm pretty certain that most of these signals should be pretty close to what we need. We may need to tweak them a little bit later. So it looks like the configuration of the Complex PLD here is pretty reasonable, and so I'll take the logic analyzer off this, and then we will hook it up to the rest of the board here. So I need to wire in the horizontal sync, vertical sync, the dot clocks over to here, and then we should be in a position then to plug this into the rest of the Breadboard PC and start to do some test software. Okay, so just taking out the logic analyzer signals, so they're scattered around the board there. quite a few connections there. Then we're going to disconnect the logic analyzer clock inputs into the horizontal sync and vertical sync for testing. Now we're going to connect up the inputs from the CRTC for the horizontal sync and vertical sync, and then the outputs from the Complex PLD for the horizontal sync and the vertical sync. Then we need to do the dot clock into the video DAC P clock. A bit fiddly, and I had to disconnect one of the 5-volt leads there, so now I need to put the 5-volt lead back in there. Okay, so I've fitted the CGA video controller into the rest of the Breadboard PC, and we've got the keypad, the 7-segment display. There's the programmer for the 1508 Complex PLD over here. I'm just going to test it out before I wire in all of the CGA card there, because just want to make sure things are working okay. So can we go to memory? Yep, that appears to be working. Can we go load? Go, yep. Okay, so that appears to be working okay. So now I'm just going to wire in the data bus, the address bus, and a couple of the control signals. So if you just have a look in the schematic to see what those signals are. So this is the CGA video controller, and what we've got coming in, we've got the data bus. Now this is going to be wired into a buffer there, but for the moment we're just going to wire it straight over here until we've actually connected up the buffer. We're also going to need to connect the address lines into this decoder, IO read, IO write, and the IO3XX sort of IO chip enable. And then there's just going to be a couple of other signals. I think the reset will need, the data transmit receive we don't need at the moment until the buffer's installed. We just need to plug those in, and then I've also got a test program. So here's a test program based on the original CGA test from the previous series, version 1 series. What we're going to be doing is loading the video digital analog converter, and we're going to be loading up the palette entries. So there's going to be 16 colours and 16 greys, although the grey is just 4 colours repeated 4 times. Then it will be outputting to the CGA control register, which at the moment isn't wired up, and then we'll be outputting the CRTC table. So these are all the register values that we need for the 80x25 text mode. And here's all the various colours for the video palette. So all this is going to do is just to initialise the video controller. Then all we need to do is to wire up some of the P0 to P3 inputs to the video digital analog converter. We'll just wire those up to some of the memory outputs from the CRTC, and that should give us our output. So just wiring in the control lines and the chip selects, and that will be the IO3XX and the reset and the CGA RAM for a bit later. This is the address lines A0 to A7 just wired in there. Then the data lines, just going to put that over to the CRTC at the moment, and then the reset plug into the PLD there. Okay, so everything's wired up, and I've done a bit of testing already and debugging. There were a couple of issues that I had made mistakes. So part of the wiring for the little variable resistor for adjusting the video intensity wasn't wired in properly, so the video was coming out a bit dim. The 2 address lines that are coming around here are wired into one of the address buffers here. However, at the moment I haven't wired these up, they're not connected to power. So all I've done is I've wired 2 address lines in and just shuffled the cables down a bit. Just need to remember to rewire those into the buffer here when we enable that. I needed to ensure that the reset signal was plugged in, and I'd also missed out the character clock coming from our Complex PLD there over to here. And I'd also made a mistake on the chip label for the decoder here, in that the CRTC chip select is actually up here, not down here. So I had to change the wire there to over there. So that's all sorted out. So I have got the logic analyzer connected to this and the oscilloscope. So what I'm just going to do is to compile the test program. Been a few minor changes to that as well, so I'll just go through that. So I've made this relocated to the code segment 6000 rather than 700. I was finding that some bits of code are being overwritten by something I'm not entirely sure what, but by moving it down, then that fixed everything. At the moment, I'm not displaying anything on the 7-segment display for the testing. When I was calling the get key in the monitor, it was causing some problems, so I need to look into that. But we've got the CRTC loop, so this reads the values for each of the CRTC registers, which we've covered previously. And then we've got the digital analog converter palette loop. What this basically does is read through the table of red, green, blue values. There's 32 of those, 16 for the color, and then we've got 16 for various grey values, which are repeated 4 times. So there's 4 values repeated 4 times. That means if we want to run in black and white mode, then it'll just come out in shades of grey. And I did also include a bit in here to read the red, green, blue values back in again. I was having some problems, and in fact what I found was that without an additional no-op between the code up here and doing the out statement, when I came to the outputting the green, for some reason the CPU wasn't outputting an IO write. So I included an extra no operation code between the instructions leading up to the out statements. And what I was finding is that it would output the red value okay, but then although it was actually processing the out instruction for green, it wasn't actually doing an IO write, and then it would just output the blue value, and that would get the video digital analog converter all messed up. So by putting a little bit of an extra delay, then that seems to have fixed that. I'm not entirely sure why the CPU wasn't outputting an IO write. It seemed to have all the right instructions. That seems to have fixed that. And then we're also then reading in the red, green, blue values just as a debug test. We'll be able to see that in the logic analyzer. I'm just going to assemble that. So we should have an S record file coming out there. So now just going to turn on the PC. So you can see the nanocomp monitor has come up here. And all we need to do is to set the extra segment to 6000. So this is the segment we're going to be loading the test program into. Set the code segment to 600, and we'll go into load mode. So that's now waiting for our program. And we'll go into the terminal emulator here, and we're just going to send our S record file. Okay, so that has now been sent. So now we're going to just run that and type go 0000. Now, first of all, what I'm just going to do is to test a lot of the signals. So what we're going to do is to go to the oscilloscope and just make sure that we've got sensible signals coming out everywhere. So here's our oscilloscope. At the moment, it's just connected to 5 volts. So 0 volts will be somewhere down here, about here. That'd be 1, 2, 3, 4, 5. Probably this one here would be 0 volts. Just see what 0 volts is. Yeah, so 0 volts is this 2 up here, and 5 volts is up here. 1, 2, 3, 4, 5. There we go. So first of all, just going to check that we've got the character clock going into the CRTC. So if we look down the bottom right hand side here, we can see this is 3.1 megahertz. So this is the dot clock, 25 megahertz dot clock divided by 8. So that's what we'd expect. Just going to check some of the memory address lines. So these are the output lines going to the video RAM. So we'll just check to see we've got a value on there first of all. So that one is the MA0, so that's about 1.5 megahertz. MA1 should be half that, about 780 kilohertz. And then MA2 should be half that as well. So that just indicates that we're getting some output there. Now we're going to have a look at the RA0. So this is the row address. Now this is actually slightly lower frequency because this is at least, this will be half the horizontal refresh frequency. So that's about 15 kilohertz. That looks to be okay. So we've got the row address coming out there. And let's have a look at the horizontal sync. That's the horizontal sync, and we can see there it's about 31.5 kilohertz. And you can see the duty cycle there. It's probably about 12-13% duty cycle there. Now I'll have to change the scale when we look at the vertical sync. So you can see the vertical sync there, and you can see it's 69.686 hertz. So it's just pretty close to 70 hertz. So that looks okay. So it looks like we've actually got sensible video signals. So I'm going to plug in the video capture card now, and then we'll see what signals we get out of that. So at the moment, I've got the input leads over here into the video DAC are just connected to ground, so we'd expect to have black. If I connect it to all 1s or 5 volts, then we're getting white. Now, if I plug this into the video address lines coming out of the CRTC, then in fact, it looks like we get the video output test pattern that we're expecting. So if we just make that full screen, so you can see here, this is the test pattern that I showed earlier, and you can see that we've got black, blue, green, cyan, red, magenta, orange or brown, then a lighter grey, dark grey, light blue. So we've got all of the colours going all the way up to white there, so that's looking pretty good. Now when I first ran this and I had the variable resistor in the wrong place in the constant current source, and this was coming out a lot duller than that, so that is now looking quite good. So if we just have a quick look at the logic analyzer output, so what we've got here is the data bus D0 to D7. We've got the IO write, the IO3XX enable, so this is for the IO port range for the video card. We've also got the specific chip select for the 6845 CRTC, the E-clock signal, which is generated off the IO read and IO write, and then we've got the video palette write and the video palette read. And then these are the addresses, address line 0, address line 1 for the video palette. And so what we can see here is that when we're writing to the CRTC, that we're actually outputting register address 0, and then the value 63, and then see the next one, we're outputting address 1, and the value 50, which is 80 columns. So that's the output going to the CRTC, and you can see there's about 15 or so registers that we're outputting there. And then what we're doing is we're initializing the video palette. So to start with, there's a mask value we have to output. So FF goes to address 2. So you see address 2 on the video DAC is for that mask. But then generally what we do is we output to address 0, we output the palette address, that's 0. And then we output the red, green, blue values. So the first one is that black, so it's going to be 0, 0, and 0. And then we actually read these values back. So this is then actually reading back 0, 0, and 0. So the first one's not very interesting. But then when you look at number 1, this is going to be blue. So we'd expect the last value to be something like 3, 1. So we're writing out 0, 0, 3, 1, and then we read them back. So outputs the address to read, address read 1, and we get 0, 0, and 3, 1. And if we jump ahead to some of the later ones up here, you'll see that when we read back values, we will perhaps have some slightly more interesting values. So 3C, 3C, 1, 3. So this just shows that we're actually outputting the video DAC properly and that we're able to read it back. When I was first doing this, what I was finding is that the instruction to write the green value, it would be processed by the computer. You could see the instruction write the value to the IO port, but in fact there was no IO write coming out from the CPU for some reason. I put an extra delay in between the instructions here and it then seems to work. So I'm not quite sure why that was. Couldn't find any documentation to say that you shouldn't do IO write too quickly, but that seems to be the issue. So what we've done here, we've connected the video address coming out of the CRTC into the video DAC just to cycle through some of the colours there. And the only other thing that I have done here as well is I've got the P5 input into the video DAC can switch between colour and black and white mode. So if we just have a look at the output when we switch to that. So all I'm going to do now is to switch the P5 input from being 0 volts to be 5 volts. And you can see now that we're just getting 4 grey black and white values. You can see we've got black, a light grey, a mid grey and a dark grey. So that will mean if we wanted to, we can actually simulate running in black and white mode, should we want to. So these are the issues that I fixed. So I forgot to wire up the inverted character clock. So I wasn't getting any of those memory outputs for the addresses or the row addresses or even the horizontal sync and vertical sync. I was finding that I wasn't initializing the registers properly, and when I looked into it I found out that the schematic was correct but the label on the CGA decoder was incorrect, and so the chip select, the CRTC, was in the wrong place. As I mentioned, the address lines A0 and A1 going to the video DAC and CRTC were connected to a buffer which has not yet got any power connected to it, and there were no address connections, so I just hooked in some connections temporarily for that. And then finally the constant current source variable resistor wasn't wired in, and so it was giving a value of probably about 10 ohms rather than 15 ohms, which is a bit too dim. So that's been fixed. So this is the pattern that we were expecting. And this is the pattern that we're getting. Switch back again. So hopefully it's indistinguishable. So that's what we would expect to get. So I'm going to finish the video now. What we're going to be looking at in the next video is programming the character generator EPROM with character sets, and we'd be looking to try and get the basic character raster output from the CGA video card. And we'd expect to see something like this. So if you don't want to miss out on future videos and miss out on the next video, please hit subscribe. And if you could hit like, it just helps to make the videos available to more people. Thanks for watching.